The following problem is an example of static equilibrium. An object is said to be in static equilibrium when it remains constantly motionless throughout time. In static equilibrium, the sum of the forces must be zero. If it wasn't, then the system would be accelerating. There must also be no motion. So the velocity of any objects involved should be zero, and the acceleration should be zero as well. Below is an example of static equilibrium. It's a weight hanging from an arrangement of strings. The drawing reveals a free body diagram for the system of particles at the junction of all the ropes. So here we can think about just a tiny piece of the rope junction being the system. And these will be the forces that particle feels. The cable at the left exerts a magnitude of force of 30 newtons. We want to find the value of the tension force T2, and we want to find the value of the force pulling downwards, and that's F. All right, one of the first things we want to do with a problem like this is we want to get rid of any forces that are at unusual angles. We want all our angles to align with the x and y dimensions. Luckily, two of these forces already do align with the horizontal and vertical dimensions. That would be F and T1. But we can see that T2 is not aligned with the x and y axis. So we want to resolve it into its components. This is a technique that I had done a video on in the past. We want to find what could be called T2x and T2y. This is T2. Let's also label that T1 is given to be 30 newtons. We also see that this angle is 30 degrees. And by complementary angles, both of these angles have to add up to 90, so that means that the other angle must be 60. Okay, now, since we're in static equilibrium and the sum of the forces is zero, that implies that the sum of the forces in the x direction is zero and the sum of the forces in the y direction is zero. We should now redraw the system completely, and let's get rid of the old T2. We've redrawn the system with equivalent vectors. T2y and T2x will add to equal T2. So we don't need T2 anymore. Now this lets us see that if T1 is 30 newtons, then T2x has to also be 30 newtons. It's the only way that we could achieve the sum of forces in the x direction being zero. And just to prove this, what we can do is write a sum of forces. T1x plus T2x equals 0. Now why did I add the x to that? Well, see, when we just have T1, then we're talking about the magnitude of T1 without regard to direction. If I put an x down, though, now the sign can tell us the direction. So T1x can hold a sign inside it, which could be a positive or negative. Whereas T1 would always be positive because it's a magnitude. There's a subtle difference there, but that's the notation that I'm going to use. Let's plug in T1x. Because we're considering the direction now, we write negative 30 newtons plus T2x equals 0. And we'll actually use this sum of forces idea to solve for the unknown T2x. It should be clear by algebra that T2x is going to be 30 newtons. Okay, now that we have that, we want to find the magnitude of T2 from what we know so far. Now it's up to you how you want to do it. You may wish to use your own triangle. So just trace this down. We created a right triangle where one leg of the triangle is 30 newtons and then the angle of that triangle is 60. So we can use SOHCAHTOA at this point. Cosine of the angle would be the best formula to use here to find out what T2 is. So I'll just do that over here on the side. Cosine of 60 equals the adjacent over the hypotenuse. And now if I just multiply across and then divide by the cosine 60, this will tell us the magnitude of T2. It's 60 newtons. Okay, that's one of our answers. But now we're also asked to go on and find the force F as well. Now that we know that T2 is 60, we could use that to find T2y. And remember, this leg of the triangle is going to be equal to T2y, so we could actually just use that same triangle if we want. And we could use a sine now instead. Sine of 60 equals the opposite over the hypotenuse. So we'll get this. And it's 52 newtons. Okay. Now that we know that T2y is 52 newtons, then it should be clear from our diagram here what F has to be. In order to achieve equilibrium, where the sum of the forces in the y direction is 0, F also has to be 52 newtons. Now I can prove that by just writing out a sum of forces, T2y plus Fy equals 0. Now why did I attach a y to the F? Because once again, F refers to the magnitude or size of the force. It doesn't include the direction. When I attach a y to it though, now we are considering the direction. So I'll put 52 newtons here. I'm going to move that to the other side through subtraction. And then we'll divide by a negative to reveal that Fy is negative 52 newtons. That's great because it tells us that the force is directed downward. And that's our final answer.